All right, guys, this is the beginning of chapter 1. Pretty simple um, lecture here about moles and equations, specifically molar mass and average molar mass. So we're going to talk about the masses of atoms and molecules. So we know everything has matter. Matter has mass. So atomically, everything is based on carbon-12. So the relative atomic mass is the mass of an atom based on carbon-12. The isotopic mass is the mass of an isotope based on carbon-12. And then the relative molecular mass is the molar mass of a molecule based on carbon-12. And the formula mass is a mass of an ionic compound, so formula unit based on carbon-12. So all these have in common is what you really need to know to determine mass. Is the periodic table. So you can find all these masses, and what you notice is that all these masses have an average. So the relative atomic mass, this is a kind of important definition they like to ask in AICE, is that it's the average mass of occurring atoms of an element based on the mass of carbon-12. So you notice that all these molar masses are decimal. So how do you get exactly 12 units? It's because of the isotopes. So an isotope is the same number of protons with different neutrons, so you get different masses. So we already talked about this in chapter 2, but the mass number is the protons and neutrons together, and the atomic number is the number of protons. All right, so the relative mass of one molecule, or the molecular mass, is basically what we know about molar mass. So for formula mass is ionic compound, so it's the molar mass of a ionic compound. So just different terms pretty much meaning the same thing. So molecularly we have water, C2H6, nitrogen. You can find the molar mass of those. It'll be molecular mass, where ionic compound will be formula mass. So you should be able to get these from the periodic table. Water is roughly 18 grams per mole, and so forth. And you should get magnesium sulfate to be 120.34 grams per mole. Accurate relative atomic masses. So how do we get these masses? So what we have is a mass spec, or mass spectrometer, and it measures the mass of each isotope and how much is percent of that isotope is in that element, and that compares how much each isotope is present. So for example, here is a mass spec graph showing that zirconium 90 is the highest percent, a little over 50%. So that means its isotope 90 is about 50% abundant of all the zirconium atoms on the sample. And then 92 and 94% are 92 and 94 masses are roughly the same, and then the heaviest one at 96 relative mass is near the lowest percent. So even though it's the heaviest, it's the lowest abundance. So how's a mass spec work? Basically, it ionizes, so it vaporizes the sample, and it accelerates through a magnetic field, and that magnetic field causes deflection. And the more it deflects, the heavier it is. Less deflection, the lighter it is. Sorry, other way around. More deflection, the lighter it is, and the less deflection, the heavier it is. And as they deflect, they can tell you how how much the sample is present. Here is another graph of magnesium, where magnesium most abundancy is 79% of a mass of 24, and then the heaviest one at 26 is 11%, and the middle one, 25, is 10%. So those are isotopes: isotope 24, magnesium 25, magnesium 26, at different abundancies. So if you want to know what isotopes are present in what percent, you can find the relative atomic mass using this information. So we can find the overall mass, molar mass of this atom based on their percentages. So we take magnesium 24, magnesium 25, and magnesium 26, and we multiply each one by their percent. So 79% of 24 is 18.96, 10% of 25 is 2.5, and 11% of 2.6 is 2.86. Then we take all those together, and you get 24.32, and sig figs 24.3 grams per mole. So that's how you get the mass of the average mass of an atom or a molecule or whatever. That's the molar mass you find on the periodic table. All right, so here is a quick question for homework. Write the isotopic formula for the heaviest isotope of germanium from that graph. And then using the abundances and their masses, you can find the relative atomic mass of germanium. All right, like I said, pretty quick, 7 minutes. We'll have more practice on this, and if any questions, let me know.